Today, on Guess What I Found Out, we need to talk about a number. Nearly 10 million people die from cancer every year. Not because treatment doesn't exist. Because, well, by the time most people find out they have it, the window for effective treatment has already closed. Caught early, survival rates for many cancers exceed 90%. Caught late, they drop below 10%. Same disease, wildly different outcome. The only variable is timing. So why don't we catch it early? Because cancer doesn't announce itself. It grows in silence for years. When symptoms finally appear, you're not catching it early, you're catching it mid-crisis. Every detection method we've developed has been really a race to shrink that gap. And until very recently, we've been losing. For most of history, detection was purely reactive. You noticed something wrong, went to a doctor, and learned you had a problem that had probably been developing for a decade. Imaging helped, but required suspicion to trigger a scan. Tumor markers like PSA for prostate cancer and CA-125 for ovarian cancer gave us something to measure in blood, but they're ambiguous, often elevated for benign reasons, and weakest at exactly the stages where catching cancer matters most. The signal scales, with tumor size. The test improves as the tumor grows. That's, backwards. Genetic approaches looked more promising. Circulating tumor DNA, fragments of cancer DNA shed into the bloodstream, enabled multi-cancer tests from a single blood draw. Grail's Gallery test screens for over 50 cancers this way. Impressive. But ctDNA sensitivity at stage 1 sits around 16.8%. Early tumors just don't shed enough DNA to be reliably detected. Still the same core problem. The test gets better as the cancer progresses. If you're the kind of person who finds this stuff genuinely fascinating and a little bit infuriating, now is a good time to like this video. What we needed was a signal that doesn't scale with tumor size. Something the body produces early and amplifies on its own. That's where microRNA comes in. MicroRNA, or miRNA, are tiny molecules, roughly 20 bases long, that regulate gene expression. They don't code for proteins themselves. Instead, they control which genes get activated and which gets suppressed. Cell growth, division, death, really all of it, runs through networks the miRNA help manage. Cancer disrupts these networks, and the disruption shows up in the miRNA profile of affected cells. But here's the part that makes miRNA genuinely powerful as a detection target. Cancer broadcasts this disruption outward. Cells communicate using nanoscale packages called exosomes. Cancer cells alter their exosome contents, loading them with a modified miRNA mix and sending them to cells throughout the body, the liver, bone marrow, bloodstream. Those recipient cells change their own behavior in response. The signal propagates system-wide. What started as a molecular disruption inside a small cluster of abnormal cells becomes a detectable signal in circulating blood, even from a tiny early-stage tumor. The body is effectively screaming. The challenge has been learning to hear it. That's what Exenera is trying to do. The company has built a multi-cancer blood test targeting miRNA across a range that includes lung, stomach, prostate, ovarian and bowel cancers, among others. The detection method is quantitative PCR, or qPCR, the same gold standard amplification technique behind COVID testing. Blood is drawn. RNA is isolated and converted to DNA. The sample is cycled through 30 to 40 rounds of amplification, doubling the target sequences with each pass and quantifying them via fluorescence. The technical hurdle is that miRNA's tiny size, roughly 20 bases, is about the same length as the primer sequences used in qPCR, which historically made the technique unreliable for this application. Exenera's proprietary solution adds a target-specific extension step that allows the platform to distinguish specific cancer-associated miRNA with precision. That's the core innovation. Follow Guess What I Found Out. If this is exactly the kind of content your algorithm should have been surfacing years ago. The training dataset covers Well, roughly 21,000 patients across 12 cancer types, including non-cancer diseases, to help reduce false positives. Feature selection identified the 50 most predictive microRNA signals. Those 50 dimensions are then fed into 2 machine learning models: a support vector machine that determines whether cancer is present, and a neural network that predicts the origin site. Case control results show 99% sensitivity and specificity with 96% accuracy in identifying the tumor's origin. Now, real-world performance in asymptomatic population trials will, of course, be lower. That's expected and perfectly normal. But achieving 99% in controlled conditions is certainly a strong foundation. NHS trials are currently underway for bowel cancer and 11 additional types, backed by £2.4 million in funding. At the same time, FDA and EMA regulatory pathways are being pursued in parallel. The economic case is, well, pretty direct. The United States spends around $35 billion every year on cancer screening. Early and accurate detection could actually cut that by an estimated $11 billion per year, while at the same time improving outcomes for millions of patients who, right now, just don't get diagnosed until it's too late. So, which detection breakthrough do you think would change the most lives? Drop your answer in the poll below. And if you've got a fact about cancer biology or early detection research that you think belongs on this channel, do leave it in the comments. Who knows, your fact might just become a future video. The story of cancer detection has always been really a story about signal and noise. Tumors are not quiet. They disrupt biology at the molecular level from very early on. The real challenge has been finding a way to listen early enough, precisely enough, and at a scale that actually makes routine screening realistic. MicroRNA might just be that signal. Not because it's simple, but because it's early, it's amplified. And crucially, it's detectable using infrastructure that already exists in clinical labs all over the world. The trials are running, the data is coming. And if the numbers hold, this is honestly one of the more consequential things happening in medicine right now. So do explore the rest of the channel. There's a lot more where this came from.